Hello, friends. Welcome. It is chapter 6. I'm Dr. Maya Dune. Here we are studying about the chemical bonding. This is the part 1. So I will explain you. What is the chemical bonding? So here you will see the octet rule. What is octet rule? We already discussed. Yeah. So the octet rule, it says always atoms or why they lose electrons, share electrons, or gain electrons to gain the noble gas configuration, because noble gas configuration has fully filled orbitals and they're stable. So here I have shown you fluorine. Fluorine has 7 electrons. By sharing 1 electron in each atom, each fluorine atom in a molecule gained 8 electrons. So that is the fluorine molecule. So Lewis structure represent covalent bonding. So this is how you draw a Lewis structure of water. So you see oxygen has 6 electrons in the valence shell because oxygen is a group 6 element. So oxygen need 2 more electrons to go to the closest noble gas, so each hydrogen share 1 electrons each to go to the noble gas configuration. Same with carbon dioxide. I'll come to the carbon dioxide later in detail. And there is sometimes they form multiple bonds, and then can be single bonds, double bonds, triple bonds. Single bond is like this, sharing 1 pair of electrons. Double bond sharing 2 pairs of electrons. In other words, it's 4 electrons, and triple bond sharing 3 pairs, 6 electrons. So bond length is important when you have a single bond. You see the bond length for these carbon nitrogen. I don't see the carbon. Okay, so let's see this one nitrogen. Single bond length is 147. But if you think about triple bond length, it's smaller. That means triple bond is more stronger. So the two atoms that involve in the bonding are close to each other. So that's what I explain you here. And then the shorter multiple bonds are also shorter. The shorter the multiple bonds are also stronger than the single bond. So always the bond length is smaller, the bond strength is bigger as well. I am moving to the next topic. Before I'm coming to the structures, it's electronegativity and polarity. What is electronegativity? Electronegativity is affinity towards the electrons. So, do you think metals or non-metals show more electronegativity? More electron loving is non-metals, right? Because always metals lose electrons, but non-metals gain electrons. So if you think about periodic table, when you go from left to right, electronegativity increases. The highest electronegativity species in the right side of the periodic table, and the most electronegative element is fluorine. So let's talk about covalent bonds. Covalent bond always share electrons. And then ionic bond, they completely transfer the electron from metal and a non-metal. So covalent bond, you can classify the covalent bonding mainly pure covalent bond, polar covalent bond. What is this polar covalent and pure covalent? Think about chlorine, Cl2. Cl2 is considered as pure covalent because when forming chlorine molecule, the electrons are shared between these chlorine atoms, but the electronegativity of each chlorine atom is same. It pulls the equal strength. So the pull towards these electrons and equal strength towards this chlorine. So these 2 electrons in chlorine, they share equally. So we call that as a pure covalent bond. Think about something like water. Water, oxygen and hydrogen. Which one is more electronegative? Because when you think about go from the left to right side, oxygen is more electronegative, so oxygen pulls electron clouds towards itself. So because of that, they're not sharing that electron equally, so that gives little bit more negativity, even though they're sharing, a little bit more negativity to oxygen, little bit positivity to, we call that as a partial negative charge to oxygen, partial negative charge to, partial negative charge to oxygen, partial positive charge to hydrogen. So we call that as a polar covalent bond. Ionic bond, oppositely charged ions held together by electrostatic attractions. So this is the electronegativity and polarity. You can see and see this is hydrogen, electrons share equally because both atoms have the same electronegativity. Think about it. Hydrogen fluoride, fluorine is more electronegative. So fluorine pulls electron cloud towards itself. Sodium fluoride, it's ionic. It's not sharing anymore. Completely sodium give away its electron. So that's the, so this is three types of bonding. Even the covalent bonding you can classify. Non-polar covalent, you will see. Non-polar covalent, pure covalent, they are same, and the polar covalent. So polar covalent always has the electronegativity difference between the two atoms involved in the bonding. So this periodic table is important. This periodic table shows the electronegativity. In all the atoms in the periodic table, there's a electronegativity. This table shows you electronegativity of each element in the periodic table. If you see closely, you see this blue color are high electronegative elements. This light greenish color is less electronegative elements, and the basically is metals, non-metals, and metalloids. So if you see, how do you know electronegativity difference? Let's take hydrogen. H2. Difference is that you take the electronegativity is arbitrary value 2.1 minus 2.1. Electronegativity difference is 0, so equally share. Think about HF. This one, HF. Hydrogen electronegativity is 2.1. Fluorine is 4. You subtract. Electronegativity is 1.9, right? So this is the electronegativity difference of 1.9. So electronegativity with atomic number always increases when you go from left to right on the periodic table. So how do you know when you're looking at the molecule, what type of bonding is that? So we say the electronegativity, so when two atoms form bonding, the bond between atoms whose electronegativity differ by less than 0.1, 0.5, sorry, is generally considered purely covalent or nonpolar. So if the electronegativity difference is 0.5 or less, it we call it as pure covalent or nonpolar. The electronegativity difference is 0.5 to 2, it is polar covalent. The electronegativity difference is 2 or above, we call ionic. So you need to know this. So electronegativity difference 0.5 or below, pure covalent. Electronegativity difference between 0.5 to 2, it is polar covalent. Above 2, it is ionic. So I have a question here. Classify the following bonds, non-polar, polar, or ionic. The bonding in CLF. So let's look at so you may wonder, how do I know these things in the periodic table? You get to bring the periodic table with electronegativity. So chlorine and fluorine CLF. So its electronegativity difference is Cl and F. It's, get the bigger number, 4 minus 3, 1. So it's a polar covalent compound. My other compound is cesium bromide. I took the cesium. I see cesium here 0.7. Fluoride 4. 4 minus 0.7. It's 0.33, right? Yeah, it's 0.33. Let me do it again. Yeah, 0.3. So it's 4 minus 0.7. Yeah, 0.33. It is above 2, so it's ionic. And then carbon-carbon double bond in C2H4. So in the its two atoms are identical, so it's a pure covalent because it's the same atom. When the bond involved in the same type of atom, it's mainly pure covalent. So that's about the electronegativity. It's an important topic. Electronegativity, you need to know by looking at the molecule what type of bonding is that. So for that, you need to know that numbers 0.5 or below, pure covalent 0.5 to 2, polar covalent above 2. It's ionic. So now I am moving to my next topic, dipole moment, partial charges, percent ionic character. The the delta sign, I told you, when there's the bonding between two atoms, mainly covalent bonding, if there is electronegativity, see, fluorine is more electronegative because it's more electronegative, it pulls electron clouds towards itself, resulting partial negative charge on fluorine and partial positive charge on hydrogen. So that is the partial charges. And then dipole moment, you calculate the dipole moment in this way. Dipole moment equals charge, and the R is the distance between the charges. Mu is the it's constant, it's always positive, expressed in this number. So that is the dipole moment. That's how you calculate. So dipole moment Q, mu is Q and R. So I'm not going to ask you really calculate the dipole moment. I just want you to have some sense of what is the dipole moment is. So percent ionic character, just know what is percent ionic character, but I'm not going to go into detail, okay, calculate the percent ionic character, those kind of things, not much. So, and then I'm going to the drawing Lewis structures. Drawing Lewis structures, very important to know, because you use drawing Lewis structures in the future chapters and if you do Gen Chem 2, and it's very useful, very important. So drawing Lewis structures, always when you draw Lewis structures, there are some rules that you need to follow. Very first rule is, for me, that in the textbook it says the least electronegative atom is the central atom. So the least electronegative atom is a central atom. Think about hydrogen. Think about water, H2O. What is least electronegative? Hydrogen, right? But it's not the central atom. Central atom is the atom where all the other atoms attach to. So there, the central atom is oxygen. So there's an exception. When you have the hydrogen in the compound, always hydrogen goes to the terminals. And then so then you identify the center atom, then you calculate the valence electrons. Valence electrons are number of electrons in the outermost shell. For each bond in the skeletal structure, subtract 2 electrons from the total valence electrons. So then once you calculate the valence electrons, first you try to so you attach the other atoms to the central atom and you try to fill the electrons in the first outer atoms. First you try to give the octet to the outer atoms, and then finally you look at the center atom. When you look at the center atom, you see whether these atoms. Okay, so in drawing the Lewis structure, so you need to follow all these instructions. So let's see in practical, how do you draw Lewis structures? So I have to draw the Lewis structure for chlorate, chlorate anion. So let me take the drawing Lewis structure for chlorate. So here, let me get a new sheet. My Lewis structure is chlorate. Now, my first step, identify the center atom. Chlorine and oxygen, when you compare the electronegativity, I have the electronegativity of chlorine. It's chlorine electronegativity 3, oxygen electronegativity is 3.5. So the least electronegative element goes to the center. So in that way, chlorine goes to the center. So chlorine is going to the center. Now my next step is adding valence electrons. Chlorine brings 7, oxygen brings 6 into 3 plus 1. So 6 into 3, 18. And then plus 7, it's going to be 25 and 26. So 26 valence electrons. I have chlorine. So this is my chlorine, and then I have O, O, O. And then this oxygen, why this 1? Because I have the negative charge. That's what I had 1. And then I distribute my 26 valence electrons 1, 2, 3, 4, 5, 6. This bond goes to 2 electrons. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 19. So now I have 24 electrons gone because this comes 8, 8, 8, and then I have 2 more. I put it here. Now I look back the center atom. Center atom also has 8 electrons, so my structure is good. Because it's an ion, I put my parenthesis and the negative charge. So this is how I write the chlorate Lewis structure. So this shows you in detail how to draw the Lewis structure of chlorate. And let me get another so you can look at it step by step. And then there are so many other compounds we can draw Lewis structure. Example, if I take water, Lewis structure of water. Central atom should be hydrogen, but hydrogen always go to the terminal. So oxygen is a central atom. Then you calculate the valence electron. This is 6 plus 2, it's 8. Oxygen, hydrogen, hydrogen. 2, 3, 4, 5, 6, 7, 8. So this is the oxygen Lewis structure. Same way, I wanted to show you the carbon dioxide Lewis structure. You know, carbon is less electronegative, oxygen is highly electronegative. So then you calculate the valence electrons. Carbon brings 4, oxygen brings 6 into 2, 12. So it's 16 to total. Carbon, oxygen, oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now my terminal atoms are good, right? All 8. Now I look at the center atom, which is carbon at this time. My carbon does not have 8 electrons. So how do I do it? In order to make 8 electrons, I have only 1, 2, 3, 4, 4. They're going to share the electrons, like both structures. So then I write like oxygen, oxygen, and then because it's share 2, I have 1, 2, 3, 4. 1, 2, 3, 4. So this is the carbon dioxide Lewis structure. That's it. I stop at that time, say, okay, I'm going to come back to the carbon dioxide Lewis structure. And I have another example here. Draw the Lewis structure of carbon disulfide, CS2. I'm going to do the CS2. You know the least electronegative atom is carbon, and I have sulfur. Sulfur, I add the valence electrons, which is 4 and 6 into 2, which is 6 into 2, 12, plus 4, 16. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now the carbon doesn't have, it's very similar to carbon dioxide. They share here, and then you get 1. Yes. So this is the carbon disulfide structure. And then I go down to the formal charge. Formal charge also important. When there are certain structures, you can draw more than one Lewis structures. Example, we're going to come to the sulfates and nitrates. So at that time, to find the most possible, more stable Lewis structure, you will use the formal charge. To find the formal charge, when there's a compound, you have to find the formal charge for each and every atom in the compound. The formal charge is valence electrons of that atom and associate all the associate electrons. Determine the associated electrons, all the non-bonding electrons, half of the bonding electrons. So you subtract all the you take the valence electrons of that atom, subtract the non-bonding electrons and half of the bonding electrons. So this is ozone. In ozone, to find the formal charge of each and every atom, the valence electrons, and then so they take each and every oxygen. So they take first oxygen. So in this first one, this oxygen, number of valence electrons, oxygen, or you don't have to look at the structure. Valence electrons 6 minus non-bonding electrons 4, right? You see 4 non-bonding minus bonding 4 half 4. So you get 2. So then this is 6 0. So this one, well, the formal charge is 0. I'm looking at this middle one now. I'm going to use another color for the middle one. Valence electron 6, non-bonding to half a bonding. So bonding, it's you have 1, 2, 3, 4, 5, 6, half into 6. So then 3, so then it's 6 minus 5, 1. This one, positive 1. And then I'm having another one, which is the last one, which is 6 minus non-bonding, 6 minus half, 2, and then it's going to be 1, negative 1, 6. So it's negative 1. So this is how you calculate the formal charge of each and every element, the atom in a compound. And then there's a question. So the widespread use of fertilizer has resulted in the contamination of some groundwater with nitrates, which are potentially harmful. Nitrate toxicity is due to the primarily of its conversion to body nitrite, which interferes with the ability to just all information. Determine the formal charge of nitrate. Determine the formal charge each atom in the nitrate and ion. So now, so in order to do that, you take the nitrogen, you have oxygen, O, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So you have all these. And then, so here, this nitrogen atom, you do, 6 minus half. So because 6 is the valence electrons of oxygen, 6 is the non-bonding electrons, and minus half minus 2 because this one bonding pair, that is 2 electrons. So 6, it's negative 1. You go to this nitrogen in the middle, 5 valence electrons minus no non-bonding, all bonding. How many bonding? 1, 2, 3, 4, 5, 6, 7, 8 to 8, 4. So this one is positive 1. And then, and you look at all the, so this oxygen also negative 1. And then we have to find this one. This oxygen, what is the formal charge? So 6 valence electrons minus 4 non-bonding minus half 4, right? So 2, this is 0. So then, in order to find the formal charge for the whole compound, what do? You add it. So this is negative 1 is negative 2, and then this is positive 1. So the total formal charge of the compound is negative 1. So that's how you find the formal charge of each and every compound. Okay, so we're gonna go to the next section. So the Lewis structures and formal charges, always when you have two possible structures, if I ask you to draw carbon dioxide, you may wonder why I'm not drawing this one, because in the carbon dioxide, carbon, carbon, oxygen, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So now this carbon has four bonding. You need four electrons. You need four more. Why this carbon can get electrons from here? And then C, 1, 2, 3, O, 1, 2, C, O, 1, 2, 3, 4, 5, 6. Why not this one? Because this structure has lot of formal charges. Always the stable structure has less formal charges or smallest formal charge. Smaller the formal charge, more stable the compound is. If you go here, the formaldehyde, which can be used as a preserved biological specimen, is like this. And then use the formal charge to determine which skeletal arrangement is better for formaldehyde. So what do? You draw the Lewis structures for this. You fill it, and then you see, okay, this has only two bonding, so you need to add more so that you have to complete the Lewis structure. And then when you get these two structures, you calculate the formal charge of each and every atom in the compound and add it and see which structure has the smallest formal charge would be the stable structure for formaldehyde, and it shows the structure is more stable. So that's the end of this section, and I'm going to stop the part 1 from here.